Okay, ladies and gentlemen, let's double check to see if the audio is working. Yeah, everything's working. Everything's online. Good. So let's go back and take a look at what's going on. So you guys remember here, all of your lectures are what? They're on Canvas. Now let's test. How do you find them? Go to modules. Scroll to what? Lectures, and then they're listed by how? Good. What's today's date? September 19th. Do you see it there? Good job. Okay. Also, ladies and gentlemen, I got to make a couple of announcements here. I sent you guys some things yesterday. Okay. So, I sent this to all my students here in my classes. We do have some mental health services that are free. So if you have any sort of concerns for your well-being, you're feeling lost or out of control, I do have that link there. You may want to click on that and do some reading. By the way, it was even on the module section here. Remember this? Mental health care for students. So there you go. So it was already there from the start along with all the other things, to let you guys know. Also, as an announcement, we need a note taker in class. I sent that to you guys. So if you're interested in being a note taker for the DSPS office, please do. We have a need in class for a note taker. So I included that flyer as well. So you could contact the DSPS office. This is all on behalf of a fellow student, okay? So essentially what happens is you take your notes on NCR paper, and then that stuff you get to share with a fellow student, okay? And this, remember the internet, we got to be careful. This time of day, internet gets slow. There we go. All right. So here we are. This is for you guys. You could contact me or the DSPS office, okay? And here's the phone number, and here's the location. But yes, here's the announcement. The DSPS service would need your assistance. A note taker is needed for this course to assist a student. If interested, we would like to provide you an incentive, a letter of commendation from the VP of Student Services, and a gift at the end of the semester, providing that you have been cleared by the DSPS office to become a note taker. We provided a notebook for use, which utilizes NCR paper. Once each class session is completed, you return the notebook to the student and remove your copy of notes. Easy peasy. So you may choose to use your own paper, but you will be responsible for providing a photocopy of your notes to the DSPS student. If you're interested in an incentive as well, as in insisting one of your fellow students, please come to the DSPS office in Monterey Park, E1160, phone number 323-265-8787. DSPS in Southgate, room 124, 323-357-6296. So we can speak with you. So thank you for supporting your classmate and doing something positive for yourself. So it is something that's very beneficial. It's something that's very helpful. So I highly encourage you to become a note taker if you're interested. Okay, so the information is here for you. Anybody interested in being a note taker by any chance? Let's ask you guys now. Okay, we got a few people. So make sure, thank you so much, you contact, both of you guys can do it. Call that phone number, 323-265-8787. And then, make sure you get cleared, whatever that even means. And then, let me know, and then we can move forward, okay? So there you guys go. There we go. There's our announcement. All righty. So, and also, too, to remind you guys, you had your in-class test. You're also going to have your what? Take-home test. So the take-home test portion has already been online. Yes, there are questions there, or there may be a question there that we haven't talked about yet. But we will, because this thing is due when? When is this take-home test due? Next Monday before class. So there is some time. All right? So you guys do have some time, but it is here. And again, it's a take-home portion. You don't work with each other. You don't take it to some tutors, and you know what I mean. It's a test, and you want to look at it as a test, and you want to make sure you do it by yourself, and you're not using AI and all the the weird things people are doing these days. Trust me on that. I have stories, and I won't go through the gory detail. But anyway, make sure you do this on your own because you're going to see it on your final, right? It's simple as that. Anyway, all right, you guys, good. So let's get to lecture. And there's a couple of things we want to talk about. Remember this differentiability we were talking about? What does it mean for a function to be differentiable? Essentially, is that limit exists. It's finite. So we've been looking at that limit question, f prime of a. And then I want to go through some of these notes as well. We say f is differentiable on an open interval I if it is differentiable for every number in the interval. And then these are what's called intervals, ladies and gentlemen, and they're open intervals. Okay? Interval from a to b, a to infinity, minus infinity to b. These are all the intervals they're talking about that you can be differentiable on, meaning the derivative of that exists, meaning it's finite. Okay? So it's a number. Finite is another way of saying number, right? All righty. Now, here's a very, very powerful theorem that we want to talk about. It's in terms of being differentiable and really continuity. Okay, very powerful. So here is what we're saying. If a function f is differentiable at a point A, you're differentiable at A, okay? If you are differentiable at A, then you want to know what that automatically means? That you're continuous at that point A. So if you're differentiable at a point, then you're continuous at a point. Now this goes back to, ladies and gentlemen, proofs that are of the form if P then Q. It's a conditional. So from geometry, you got this conditional, P arrow Q, where your assumption is here. This is an important point, and your conclusion is here. So conclusion and assumption. So we always start, and I got to make sure the colors are right. We always start, ladies and gentlemen, your starting point is the assumption. It's P. Okay, so they're assuming a function's differentiable. So what that means is it satisfies that definition. That's all. Assumes it's differentiable at A. Now, we're going to do a little bit of algebra here with this. Okay? So what happens is, right in here, this portion, this numerator, you know, that numerator is f of x minus a over x minus a times x minus a. And we should put parentheses there. Okay? So all we're going to do now is take the limit of the left-hand side and it equals the limit of the right-hand side. And then the limit of a product here is product of limits. So this is where we're at. Limit of product is product of limits right here. Okay, so all we're doing is limit of that difference on the left equals the limit on the right-hand side. So here's the left-hand side, right-hand side. So the limit of the left-hand side is the limit of the right-hand side, and this is what I mean by the product rule right in here. Now this portion, we know, is finite by the assumption. And we write that as f prime of a. This portion here is actually 0, because by direct sub, a minus a gives you 0. So any finite number times 0 is actually going to be 0 here. So what they're showing now is this, that the limit of the difference really is the number 0. And that's what we're writing down right here. The limit of a difference, which is now is difference of limits, and that equals 0. And so what we're showing here, this is f of a. This portion here is f of a. Apologize. since the limit of a constant is a constant, using some algebra, here's our conclusion. And I think we use the conclusion in green. That means the function is continuous at a here. Okay, so the function's continuous at a. So here's kind of the most important part of the statement here. I'm going to write it down here. Start talking about some details. Bless you. If f is differentiable at x equals a, then what we have proven is f is continuous at x equals a. All right, so if a function is differentiable at a, then it's continuous at a. That's what we've proven. It's if P, then Q. So here's where some mathematics really comes in. I think it's orange, right? If P, then Q. Now this statement, although it's valid, this is where math comes in, ladies and gentlemen. This is a valid statement. Okay? It means the conclusion is inescapable from the assumption. There's a whole thing about it's written in stone. But I do have to say, this statement by itself isn't really very interesting. It doesn't really have a lot of deep meaning. If f is differentiable at x is a, then f is continuous at x is a. That kind of doesn't have deep meaning. But here's the beauty of math. You have a valid conditional. It goes all the way back to geometry. Okay, it goes back to geometry. Now you might say, what do you mean by that? Well, every conditional is equivalent to, you say, what do you mean is equivalent to? That's equivalent to what we call the contrapositive. Okay, so if you have a conditional, that is equivalent to, here's your conditional, this contrapositive right here. This, ladies and gentlemen, is also, by the way, valid. You get the contrapositive free of charge. Now that is where the gold is. This is where the genius of proving that statement is actually used. And very often in mathematics, you have a statement that just seems a bit trivial and not meaningful, but the contrapositive is really the meaningful statement. And this is actually that situation. You just have to know what the contrapositive is. And you say, well, what's a contrapositive? Well, do you guys know what these squiggle lines mean? What's those squiggle lines? That's a negation sign. That means not. So the squiggle lines, back in geometry and logic, means to negate. That's not. So here's what that gold is. So you're going to, and you might say, did you change the colors? I did. Let's go back to the colors here, because that's an extremely vital. This is vital, the colors. We're saying is if f is differentiable at a, then f is continuous at a. Here's the contrapositive. If f is not, what's the negation of being continuous? If f is not continuous, at x is a, then we can say f is not differentiable at x equals a. That is a valid statement. This is the contrapositive. So let me get out my highlighter. This is the word not. Not continuous at A. Does that mean discontinuous? Not what? Differentiable. So not, you're inserting the word not and you're reading the statement backwards. That is called a contrapositive for a conditional. And why that's important is if your conditional is valid, your contrapositive is valid. That is extremely, extremely important. Now you might say, why? Read this again and think about it, okay? What is that even saying? If a function is not continuous at a point, then you can say the function is not differentiable at a point. So what comes to mind? In my mind, you want to know what comes to mind? If I said to you, think of what? Rational functions. What do you guys know about rational functions? Right? Remember this? P of x over Q of x. Rationals. You have vertical asymptotes where that denominator equals 0. Remember this? Okay, vertical asymptotes, you set the denominator equal to 0. What do you guys know about vertical asymptotes? Yeah. So remember this here, very often you have that x is a. If you have a vertical asymptote at x is a, well, you know then f, or the rational function, is discontinuous at what? X is a. So if it's discontinuous, not continuous, what do you guys know about that? Yes, that's all you got to know. Then f is what? Not differentiable at what? X is a. Guaranteed. Guaranteed. That's all this is saying. Okay, if you have a rational function at your vertical asymptote, you know it's not continuous. But also, if it's not continuous, it's not what? Differentiable. And if I go back to my sheet here, right, remember this stuff here, the contrapositive is valid. That's what we just gave you guys. I'll talk about this statement, but I want to go to this here and remind you guys, here's a nice simple rational function, right? How do you get the vertical asymptote? You always set the denominator equal to 0. And yes, ladies and gentlemen, it's a what? Vertical line around 0. Your function is discontinuous at 0, and it's not differentiable at 0. Even if you found f prime of a, right? You might say, oh, Mr. Judge, I went through that exercise, and I find this is negative 1 over a squared. I use the definition here, okay? And yes, maybe you said, can I put that, change the variable to x? Okay. There's your derivative. We already know the algebra. We've seen it over and over again. You even had it on your test, and okay, whatever. What do you guys notice at 0? See this here? You can't have a denominator be 0 for a function. So you're saying this is not what? Differentiable at that 0 value. There's a derivative there. So all of that is connected together. That's why I put it all together this way. Function is not continuous at 0, and it's not what? Differentiable at 0. But it's continuous everywhere else, and it's differentiable everywhere else. What do I mean by everywhere else? All the other numbers on what? See these, all these other points on the curve, which corresponds to all the points on the real number line except for 0. So it's differentiable and continuous for all other values. So you're actually finding where it's not continuous. So it's everywhere but these points. So any rational function has that problem. Okay? And you go, here's another rational function. Yes. The vertical asymptote is also at 0. So what do you guys know here? F is what? Not continuous at x equals 0. Okay. You say y. Well, look at that. The denominator. You set it equal to 0. And what do you get? Vertical asymptote at x is 0. You say, is that where it is? Sure is. So it's discontinuous at x is 0. And it's not what? So f is not differentiable. At what? At x is 0. But it is continuous everywhere else, and it is differentiable everywhere else. And in fact, if you don't believe me, I can actually give you the formula. If you did that, that's negative 2 over x cubed, or a cubed. You know, the differentiable formula there, using that derivative, is negative 2 over a cubed. So you notice again, the derivative around 0, you have a problem. All right. Okay, now this is a situation that I threw out to people. And because again, it goes back to rational functions. Where do you have vertical asymptotes? Yeah. So your vertical asymptotes, you have 2 locations, right? That happens when x times x minus 4 equals 0. Okay. So doing that algebra or pre-calculus, x is 0, x minus 4 is 0. That means x is 0 or x is 4. So remind people, your vertical asymptotes are where? Here in the picture and here in the picture at 0 and 4. So they have 2 vertical asymptotes. So what do you know? F is, can I use the word discontinuous? Right? At x equals what? 0 and x equals 4. But that guarantees f is what? Not differentiable at x equals 0 and x equals 4 as well. By that contrapositive statement. It is continuous everywhere else, and it is differentiable everywhere else. So, okay. Now, I want to remind people, I'm going to skip that for now. Remember the jump discontinuities here? I'm going to do some examples here. Okay? I'm going to do some jump discontinuities here. So here's an arbitrary picture. And I guess we can say this is 1, 2, 3. This is going to be what? Negative 4. What do you guys notice? What do you guys remember about any jump discontinuity? It is a piecewise function, but it's not continuous, right? F is not continuous where? At x equals negative 4. And you say, why? You have a jump discontinuity. Okay, what if you even said, oh, can you prove that? 1, 2, 3, 4, 5. This is 6. Well, what's the limit of this function as x goes to negative 4? What do you say? That does not exist. Is that true? Why? Because the left-handed limit is 6, and the right-handed limit is, this is 1, 2, 3, is what? 3. Is that true? So your left-handed limit doesn't equal the right-handed limit. The left-handed limit is 6, and the right-handed limit is 3 at x is negative 4. So, all right, we had that kind of stuff on the test. So what does it have to do with the theorem I just showed you today, or I should say the contrapositive? I'll put it in purple. F is what? Not differentiable where? At x equals negative 4. That's using the statement. If it's not continuous at a point, then it's not differentiable at a point. Okay, and that's, again, a jump discontinuity. And then you might even say, okay, Let me draw another kind of picture for you guys. And this will be about at 3, okay? And then we have what, 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, that's not a jump discontinuity. So let's remove that. So I wanted to do two situations, a jump discontinuity, and then what do we call this? This is a what? A removable discontinuity. We can have holes. Okay, so what do you know already? F is what? Discontinuous at what? At x at oh no. Yeah. F is discontinuous at x equals 3. That's true. And you might say why? Why is it discontinuous? The limit as x goes to 3 of the function, you guys had a test on that. This is 8. Is that true? But what's the value of the function at 3? It's undefined. Why is it undefined? There's a hole there. That means not defined. So really, why is it discontinuous? Because f is discontinuous. It's because the limit is not the value of the function, right? So limit of the function does not equal f of 3. This is as x goes to 3. Okay? That's why it's discontinuous. Okay, that was our test. What does it mean today? F is not what? Differentiable at x equals 3. Okay? All because it's discontinuous. It's using the contrapositive of that very powerful statement. Now, what you have here, let's go back. So this is removable. I think I want to go back to this. There's an example. Well, we'll go back to this example here. Now, I wrote this statement here to say to you guys, this is an invalid statement. This is where there's some confusion. I'm going to write this down here. Let me go back over here. There's some confusion here. Remember our theorem, and I'm going to erase this here. This is differentiability. Continuity implies differentiability. That's really what this is. Fall 2023. Differentiability implies continuity. Sorry. All right. Now, any conditional, ladies and gentlemen, you have an issue. A conditional is not equivalent to the converse. In other words, don't read it backwards. This is called the converse of the statement. That is not equivalent. And so you may have a valid conditional. There's no guarantee, may or may not be valid, generally speaking. And you might say, well, what does that even mean? If I go to the colors, I think orange implies green. Students think you can read this statement backwards and get away with it. You can't. that is where you have a problem. You cannot read this how backwards. It's generally speaking, it may be valid, it may not be valid. In this case, it's not valid. So let's read it backwards. Here's what students like to say. They like to think, if it's continuous, then it's differentiable. If f is continuous at a point, then f is differentiable at that point. The answer is not in general. You can't read it backwards. No good. Just because you're continuous does not mean you're differentiable. Okay, the book's example. You guys have the book? Is it helpful? Having a book? Okay. Here is the example I'm referring to, and it's even in that picture if I go back, right? So let's look at that picture. Here's a picture. What do you guys notice about the absolute value function? This is the absolute value function, by the way. Well, it is piecewise, but what I'm getting at is this. Isn't it nice and what? Continuous everywhere. If I draw that, you know. Well, yeah, so here's the thing about it. F is continuous. When I say everywhere, what do we mean? All real numbers. It's this really interval. All real numbers, that's an open interval. It's continuous for every real number. Okay, if you draw that curve, what's the deal? You never picked up your pencil anywhere. It's nice and continuous. However, you notice what's different about this curve. It has a what? A sharp what? Corner at 0. Okay. It has a corner at 0. So here's what we call a counterexample. This is why this statement is not good. Let's determine, is f differentiable at x equals 0? Okay? Well, here's the very, 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 very famous proof. It's in your book. You know. Anyway. I don't like to use that one, but sometimes you have no choice. Okay. So here's what we're going to do. Let's use our definition. This is why we have to know our definition. F prime at 0 here is the limit as h goes to 0, f of 0 plus h minus f of 0 over h. If you said, where's my a? Well, that's the a value we've been seeing in our definition. A is 0 here. Okay? So now you might say, is that the limit? H goes to 0. 0 plus h, isn't that f of h? Minus f of 0, everything over h? Okay. Well, how do I get f of h? This is h. Replace x with what? H. You now have the limit. H goes to 0, absolute value of h minus the absolute value of 0 over h. And so you might even recognize this as well. Okay? Because the absolute value of 0 is what? 0. Okay, so yes, it's a piecewise function. You know, of course, h can't be 0 here, but you're going to have to define this function. You got to know how to define that. You say, well, how do I define this particular function because we have to find the limit, right? So whenever you have the absolute value, remember that function, by definition, is this. You can say, is that h over h for h? You can't say greater than or equal to 0 because you're throwing it out, right? So greater than 0. And it's opposite h over h for what? H less than 0. So we're saying it's 1 and it's minus 1 when h is greater than 0 and when h is less than 0. So here's the function they're talking about. This is a classic demonstration for not being differentiable for the absolute value function at 0. Now for h values that are to the what? Are greater than 0, this applies to limits that are to the right of 0, right? And for those left, that's to the left, less than 0, right? So the reason that's important is because the right-handed limit now, limit as h goes 0 from the right of this function is positive 1. The limit as h goes to 0 from the left of that function is negative 1. So in conclusion, that limit, what's the story here? You guys know this already. You had a test on it. Is a what? The limit does not exist, ladies and gentlemen. So in order for a function to be differentiable at a point, what did that sheet say? Originally, we say a function is differentiable at a if the limit what? Exists. They mean if it's finite. If it does not exist, then it can't be what? Differentiable. See how that definition works here? See, definitions, ladies and gentlemen, the key to math, any math class, really the key to any topic, any subject, doesn't matter what the subject is your definitions. You take any subject, know your what? Definitions. You say, I'm going to take a subject on artificial intelligence. You got to know your what? Definitions. Without knowing definitions, you're not going anywhere. You know, I gave a trick test on like circular functions, right? In order to answer those questions, you got to know your what? Definitions. So here's the definition. If it doesn't satisfy that definition, this is where the logic comes in. What did I do? Oh, it's right over here. Here's your conclusion. What we've actually shown is that f is what? Discontinuous. Yeah, I think I had it right. At x equals 0. That's the very, 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 very famous proof of being discontinuous at 0. Sorry, I made a mistake. I apologize, not being differentiable. F is not what? Differentiable. At x is 0. That's a very, very famous proof. It's not differentiable at 0. But if you go back to that sheet, you say, okay, Mr. Judge, this is continuous at 0. I know, but it's not differentiable at 0. So this is why they say the counterexample. This is called a counterexample to the converse statement. It's invalid. So this is a classic counterexample, meaning this statement gets to be thrown out. You can't use it. It's done. Throw out that statement. You can't say that. It's not true. So you throw that. It's like if I told you every student that walks down that hall has green shoes. All you got to do to disprove that statement is find one person, only one, at a minimum one, who walks down without green shoes. You just found a counterexample to this converse statement. And that's where students make the biggest mistake. They think the converse is valid, and it's not. They go, oh, it's continuous at the point, therefore it's differentiable. Nope. Another way of thinking of differentiability, if you guys want to really think about the geometry of that statement, here's another way to think of it. It has to be what? This is another insane. It's smooth at x is a. This is another way of thinking about differentiability, that for a curve, it's actually smooth at that point. So if you have a corner, what's the problem with a corner? It's not what? Smooth. Okay, so it's not what? That's what they mean by smooth, no corners. No abrupt changes. Okay. Now, I got to find another, hopefully I find it. I'm going over the cases where you're not differentiable. So you're not differentiable at vertical asymptotes. You're not differentiable anywhere you're discontinuous. And you say, well, what's the, it's not differentiable where it's not smooth. What's some of the other criteria? This is another one we did here. Well, we didn't do this one. Although, why do you think this one's not differentiable? Yeah, it's not smooth. Is that true? What function is this? We actually did this function. Did we do that one? I think we did this function. But anyway, this is another example of not being, this is why I put them together. Additional circumstances for not being differentiable. Oh, we can look at this. There's a way to do this one. It's the same exact proof. I don't see what time we have. You could, this is not, where is this not differentiable? Right, F is not differentiable where? At that point. Where's that point at? At -5. How do we know it's not differentiable there? Yeah, there's a sharp corner. Not smooth. Could you prove it? Yeah. Absolute value of x plus 5. Right? So if that function, they might say prove. Right? Prove it's not differentiable at x equals what? -5. So how do you think you prove it, ladies and gentlemen? You use the what? Definition. What's f prime of -5? This is why I had you guys do that. This is why I went through that definition. So here's a different function. Very similar, but how do you do that? I thought of putting that on your take-home test. If I had to do it again, I would. Maybe I'll change it. What do you think? Limit x goes to -5. F of a plus h, -5 plus h, minus f of a, -5, everything over what? H. So back in the definition, this is what? A. What is this? A. All right, you guys okay with that? So notice this, the proof is the same in terms of the format. So let's see the details, right? This is the absolute value of h minus 5 minus the absolute value of -5 over what? H. And the absolute value of -5 we know is what? 5. So let's put this together. Limit x goes to -5, absolute value h minus 5 over what? Over h. Yeah, let's double check, okay? Let's see if we're doing the right definition. F of a plus h minus f of a. All right. Okay, so now we have to define that function here. So do you guys know, by the way, we have to say this function here. So you probably have to get a hold of that, right? So what is this? This is, by definition, what? It's h minus 5. Is that true? For what? H minus 5 being greater than 0. It's opposite h minus 5 when h minus 5 is being what? Less than 0. So we get h minus 5, where h is bigger than 5. We solve that, and then minus h minus 5 when h is less than 5. And you're going to throw it out because of the fact that you say, well, don't you have to have an equal sign here? But I'm going to have to plug this in. Okay, I'm going to have to plug, this is the same function. So you have to plug this portion in here. H minus 5. I think, I forget the colors, but in that, every value of h to the right of 5, and this is to the what? Left of 5. Is that right? You guys okay with that? Does that look okay? So double check here. Mm-hmm. All right, so let's see what happens now. So if we're going to find f prime, let's look at the limit. If we do the right-handed limit, let's use the green. The limit, x goes to negative 5. There's something bothering me here. There's something wrong. You guys see what's wrong? F prime at negative 5, so where's the problem here? Oh, we got a sign here. Let's go back. Let's look at this. X plus 5. That's x plus 5. Okay. Yep, we got it here. X plus 5. There it is. There it is, right in here. Okay, let me undo this here. I found it. Negative 5 plus h goes here, is that right? There it is. Okay. Yeah. So let's erase this. Here we go. That's where it's going to be. Okay. Now we got it nice and awake. So, all right, absolute value here. This is going to be absolute value of h, right? Minus, plug in negative 5 here. Absolute value of 0. There it is. Okay. So, yep, let's get rid of that. Not necessary. There it is. See when you change that sign. Okay. I apologize there. So this is going to be 0. That's where this is. Okay. Let's double check. And h goes to 0. That's where the problem is. We're using the two definitions. Okay, h goes to 0. H goes to 0. Now we're good. Limit h goes to 0. Okay. Now we're good, and you guys know that this does not what? Exist. So that one was a lot more easy peasy. We can't mix up our definitions. Okay, so this is the definition, the original definition we're using. There we go. F prime A, limit h goes to 0, f of a plus h minus f of a over h. So this is what we're using here. So as you guys can see, that limit, what again, for the same reason as the last example, does not exist. So that's all we used. So go back and plug that in and get what you see here. So the next one, though, we said, Mr. Judge, what about this situation? Right? At 0, this is nice and continuous. Like, this is continuous at 0. It's continuous everywhere, right? But it's not differentiable at -5. We just seen the proof. This is continuous everywhere. At what? It's everywhere. But we're going to see that f is going to be what? Not differentiable at x equals what? 0 at this point. Okay, now this is the function you're looking at right here. So now, again, we said we're going to look at this function, f of x, x to the 2/3, at x equals 0 here. Okay. So we're going to try to find f prime of 0. Is that right? Limit h goes to 0. Make sure we use the right definition so we don't mess up like the last one. But it's not a mistake if you find it, right? So and this is f prime of a, so we're going to plug in 0 now, okay? So plug in 0, plug in 0, plug in 0, because this is the x is a at 0. So f prime of a becomes that limit now, just using the definition. This is f of h minus f of 0 over h. So plug in h, plug in 0. Plug in h, plug in 0. This is a limit. H goes to 0. H to the 2/3 minus what? 0 to the 2/3 over what? H. Limit. H goes to 0. And isn't 0 to the 2/3 going to be 0? Okay. So h to the 2/3 divided by h to the first power. Use a little bit of what? What do you guys use? Yeah, algebra. Isn't that h to the 2/3 minus 1? And that 2/3, that's 3 over 3. So, ladies and gentlemen, this is the limit now. H goes to 0, h to the negative 1/3. And then I'm going to say to you guys, isn't that the limit as what? H goes to 0, 1 over, is that the cube root of h? Yes. Is that true? Yeah. Yeah, so you got a little bit of algebra there. So it might be easier to just use the definition from the first place like we've done here. Okay, and then change that a to 0. Okay, h to the 2/3 over h, which really is h to the minus 1/3, and it's 1 over, remember, from algebra. And then that's going to be the cube root. H to the 1/3 is the cube root of h. So does anybody know, how do you find that limit? How do you get that limit? What do I say here for this limit? This limit, ladies and gentlemen, does not exist. How do you guys know that limit does not exist? Okay, this is the key here. This goes back to yesterday. Let's say this was a test from yesterday. Double check and tell me if this is true. Did we study all of these kind of things yesterday? I mean, let me take this back. What's the left-handed limit of 1 over the cube root of h? What's the right-handed limit? 1 over cube root of h. Tell me if we studied any of this. Can you, if h is going to 0 from the left, okay, what can I use for h? A negative what? Number. Close to h. Is that true? Like negative 1 over 1,000, right? Or negative 0.0001, 10,000, doesn't matter, okay? That's for the left-handed limit. What do you think I'm going to get? Is that going to be negative infinity? Didn't we talk about all those little details? And you say, why? Because down here, if you plug in that h being close to 0, it's in the that's a small number. I know it's negative. Could you take the cube root of a negative? Yes. What's it going to be? Negative. Cube roots are still negative. Cube root of a negative is a negative number. Is that true? So that h is small. What about 1 over small? 1 over small gives you what? Does it give you small? Let's think about it. 1 over small gives you what? Large. 1 over very small gives you very large. Now, what am I getting at? Go to your TI and say, okay, Mr. Judge, I don't believe you. This is kind of the essence of that numerical approach, right? 1 divided by cube root. Where's the cube root? I'm going to put that into a power like this. Negative point. Small. I could get very, very small. Yes, it's negative. Now raise it to the what power? 1/3. Okay, it's a cube root. Yes, that's negative, but think of that as negative what? Large. This is what I'm getting at for the left-handed what? Limit here. So whenever you put a small number in the denominator, that's what I'm saying down here, small. I know it's negative. It's going to be negative. But if I put a small number, well, this is h, okay? Let me go back. This whole thing was, I'm saying, small. Okay? That whole thing, 1 over that fraction, small. H down here. I know it's negative, but think of it as negative small. Is going to be large because it's in the denominator. The next one down here, it's going to be, h is going to be what? Positive now because you're going to 0 from the right. So again, you say, can I use 1 over maybe 1,000,000 or whatever that is? Or this h is very, very what? This is very small. That very small number is going where? Where's that very small number going? It's in a denominator position. What's that going to mean? That we're going to get a very what? Large number. Because 1 over very small is very what? Large. One's positive, the other's negative. What does that mean? Does not exist. So ladies and gentlemen, we just proved that the function, this function, x to the 2/3 power is not what? Differentiable at x equals 0. So we just proved that. It's not differentiable. Say not differentiable because that limit does not exist at 0. So if I go back to that picture here for this function here, in my notes, we just proved this statement. So that statement is the function's continuous at all real numbers. In particular, it's continuous where? At 0. But it's not differentiable where? At 0. It has a what? Corner. And you think of it as kind of like a sharp corner. We in higher math, we say it's not smooth at that value. It's not smooth. So these are the circumstances where you're not differentiable. Now, I did this one. If you guys want to see the last case, here's the last case. This function is, believe it or not, it's continuous everywhere. It's continuous at 0. But this is what we call a vertical tangent. And it has a vertical tangent, really, at x is 0 here. Okay, so at 0, what do you guys see? Well, we're going to see tomorrow what a vertical tangent line is. We're going to see tomorrow. What's a vertical tangent? It's a derivative. We've already been looking at it. But we'll see that tomorrow. We call that altangent at 0. Now you say, well, what do you guys know about that tangent line? It's vertical. What we're going to see, and we already actually seen this example. I already proved it to you with a factoring by definition. I'm going to say, see your notes. I showed you guys what f prime of a is. I think it was 1 over 3a right, 1/3. This is what it was. Okay, so that is what I shared with you guys. Obviously, you can't divide by what again? At 0, so there's an issue at 0. But in this case, the limit, you're going to see this limit here, right? So that limit, by definition, f prime a is going to go to infinity. As a goes to 0. Okay, now you might say why? Because around 0, if you use the same argument I just showed you guys, get close to 0 from the left or the right. Doesn't matter. You could use that value very close, like a negative, that h value, negative 0.00001. And you go, what happens with the square? Doesn't the square make it positive? So it's 1 over very small gives you very what? Large again. And then here, h to the right, 0.00000 again, 0.00001. 1 over very small is, again, square it, it's positive. Yes, you're going to take the cube root, doesn't matter. But that squaring makes everything positive. So it doesn't matter if it's left or right. That's why it's a positive infinity there. It's not, it does not exist. So that limit has to be finite in order to say the function's differentiable at a point. This limit's not finite. So this is the examples that we went through. So this limit, you're going to say here, this is infinity. That's enough to say that limit, it's not differentiable. You could use the same argument. I see your notes for that function. We found that function. I could do the same exact stuff I just showed you guys around 0. It's the same exact thing that we just did here. You're going to see, or whatever that was at. Yeah, it's on the other paper. But that's pretty much, again, everything. And I don't have time, but that's pretty much everything I wanted to talk about being differentiable. Yeah.
If the limit does exist, does that mean it is differential?
Well, if the limit is finite, it's differentiable.
Okay.
That's the. Do you guys understand that there's a real issue with language? What the author did. If the limit is finite, what's a finite number? 2, 1,000, a billion even. Finite, negative, -6, -12. If it's a finite, then it's differentiable at that point. If it's not differentiable. What is not? What do we mean by the not? If it's infinity, or where is it at? Or it does not exist, like the one we just did. Okay. Yeah, see these? This is a does not exist. Where are we at? Here we go. So if that limit does not exist, or if it's infinity, or even negative infinity, not differentiable. The only time it's differentiable is when the limit is finite. It's the only time. And that's pretty much it about really what we mean about differentiability. Now, we're kind of out of time, and I'm going to put your homework in Canvas, but you guys have already that whatever take-home, whatever stuff is. And if I had to do it all over again, I'd do it a little different, but that's okay. It's okay. You know why? It'll be on your test what? 2 anyway. So tomorrow we're going to see that what that tangent line is, and then maybe what's the story. Maybe the last case, you can say, oh, I see what you mean, Mr. Judge, about that, and I'll go back here to it. Maybe I'll throw that one there. Show that this one, what's this limit? At 0. I might change that one. I might give you this again. It's in your notes.
Can you go over that again tomorrow?
No, we have other things to do tomorrow. What's the beauty of actually having videos? Yes, you could go back and what? Look at what you need. I'm going to say that again. Oh, my God. Not only that, I probably even have it on my what? Website. Where is my website? Come here, website. And don't tell me, because sometimes students will say that. Mr. Judge, did you say you have a website? And hopefully Elon Musk will buy it. I might even have it here. No, I don't think that's it. I'll look for it. Anyway. Okay, ladies and gentlemen, we'll see you when? Tomorrow. Have a great day. Take care and stay safe.